Welcome. Let's talk a little calculus here. Specifically, I want to talk about the derivatives of trig functions. To start off the lesson, I'm going to bring back a few maybe pleasant or unpleasant memories, whichever, of your pre-cal and the basic trig before we get into the derivatives. And here, there's a graph of the 6 trig functions, and we'll go more in depth specifically on the sine, the cosine, and the tangent as well today. So let's get started. So a few basics. If I have a right triangle in standard position, meaning with its initial side on the positive x-axis, the opposite side being my y-coordinate on the unit circle, the adjacent side being my x-coordinate, and then my r being my hypotenuse being the radius of the unit circle. Those are all some important things to know. And with that being said, we know SOHCAHTOA is sine is the opposite over hypotenuse. Cosine of angle theta is adjacent over hypotenuse. Tangent is opposite over adjacent, or sine over cosine if you prefer. And so opposite over hypotenuse is really y over r, so that's where we get our sine from. Cosine is x over r. Tangent is y over x, and then you have your 3 reciprocal functions, the cosecant, the secant, and the cotangent. Let's talk about the graphs specifically. Like I said, I want to talk about the graphs of the sine, the cosine, and the tangent, and they all kind of come back to our friend the unit circle. I'm going to label the axes. So our positive x-axis starts at 0, and then you rotate. Pi halves is your 90 degrees vertical. Pi, 3 pi, and then we know 1 complete rotation around a circle is 2 pi. So here we go. The radius of a unit circle is defined as a circle of radius 1. So if this center point is 0, 0, on the axis, the 0, 2 pi axis will be the point 1, 0. Up here at pi over 2, we'll have the coordinate 0, 1. At pi, -1, 0. And cosine 0, -1 at 3 pi over 2. And then again, back around, you hit 2 pi and you're back at 1 over 0. Or 1, 0, excuse me. So here's the deal. When we graph the sine, remember the sine was y over r. And since the radius of our unit circle is 1, that's really y over 1. Or in other words, on your unit circle, the y-coordinates here, 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 and here, and then back to 2 pi again, those are the values of your sine. Your coordinates for your x over r, which is x over 1, which is x. Your x-coordinates give you the cosine function. So here's cosine of 0, cosine pi halves, cosine pi, cosine 3 pi halves, and then back around again, you get 1 for cosine of 2 pi. Tangent is defined as y over x, or you can think of it as your sine over your cosine. So that's where I'm going to get the coordinates for the graphs from, just basic quadrantal angles on the unit circle. So sine x, again, remember sine x is the y-coordinate on the unit circle. So at 0, our y-coordinate was 0, pi halves was 1, pi was 0, 3 pi over 2 is -1, 2 pi was 0. Straight from here. Straight from this, 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 and this. That's where the values for the graph for the sine come from. Just basic manipulation on the unit circle. And then I just graph the points. So we have 0, 0. At pi halves on the x, we're at 1. pi is at 0. 3 pi over 2 is at -1. 2 pi back to 0. That's one period of the sine function. Again, it is periodic. It's going to just go on and on and on and on. So there's your sine graph. Again, your cosine was all the x coordinates on the unit circle, so I'm not going to go back to it, but cosine starts at 0, then at 1, and then at pi halves it goes to 0. Pi is -1, 3 pi over 2 is 0, 2 pi is 1. Looking something like that. And again, yes, it is periodic. It's going to continue repeating that pattern on and on and on from -infinity to positive infinity. Now the tangent's a little creepy. Remember, tangent is defined as your y over your x. You can get it that way, or you can take the values we got for the sine, divide them by the values of the cosine. You basically get a table that looks like this. And the interesting points, at least I think, are what happens at odd multiples of pi over 2. Those are where the tangent function is undefined. They are the vertical asymptotes. So these red dotted lines are going to be our vertical asymptotes at odd multiples of pi over 2. Multiples of pi are our zeros. Pi over 4 to the right is up at 1. Negative pi over 4 is -1, so there's basically our graph. And again, it is periodic. It's just going to keep doing that same thing over and over and over again. This would be at x is 5 pi over 2. So it is good to know the graphs of these, especially when we start doing some stuff with differentiation, integration, and things of that nature. Not sure if you're ever familiar with the gang signs, but it's basically a way for you to do the trig functions on your hands. It's kind of a neat little trick. If you did not have me for pre-cal, I'll talk about it in class. If not, talk to your teacher about it. They probably know it too. Okay, so let's practice. Things I need you to just, right off the top of your head, just know. If you want to practice with your gang signs, or even better, if you just know the unit circle, that's awesome too. So sine of 0 starts at 0. At pi over 6, sine is 1/2. Root 2 over 2 at pi over 4. Root 3 over 2. And then at pi, it's 1. Cosine is exactly that in reverse. Instead of starting with 0 and ending at 1, it starts with 1, ends at 0. And then I basically go in this direction. So root 3 over 2, root 2 over 2, and yes, at pi over 4, the sine and the cosine are in fact equal, and then 1/2. Now, tangent is basically, remember like I said, tangent is like saying sine of x or sine of theta over cosine of theta or cosine x. So if I take sine, which is 0, divided by 1, that's 0. Pi over 6, if I take 1/2 and divide it by root 3 over 2, that is the same as 1/2 times 2 over root 3, which gives you 1 over root 3, which you rationalize and get root 3 over 3. For pi over 4, sine over cosine, since the sine and the cosine are the same, root 2 over 2 over root 2 over 2, top and bottom are the same, is 1. At pi over 3, again, I take sine divided by cosine, or my y divided by my x. I get root 3 over 2 divided by 1/2, which is root 3 over 2 times 2 over 1, root 3. And then lastly, 1 divided by 0, or anything divided by 0, is undefined, which is why at odd multiples of pi over 2, you get your vertical asymptote. Okay, again, we've kind of talked about this already, so I'm not gonna go over that more, but it's useful info. Let's give it a shot again. So sine, remember it starts off at 0, 1, 0, -1, 0. Cosine, 1, 0, -1, 0, 1. Tangent, asymptote, asymptote, and multiples of pi are at 0. And then at pi over 4, it either goes up to 1 or multiples of pi over 4, and it's either up to +1 or down to -1, depending upon which multiple you're talking about. You probably talked about the trig identities in your pre-calc class. Just what I've found from teaching calculus for a while, there are certain ones that I see coming up a lot over and over again, and here they are. I would know my 3 reciprocal identities, that sine and cosecant are reciprocals, cosine and secant are reciprocals, tangent and cotangent are reciprocals. Your quotient identities, we're going to actually use these a lot in some proofs today. So sine over cosine is tangent, cosine over sine is cotangent. And then your basic trig identity for your Pythagorean functions or Pythagorean identities. And then this one and this one are just a branch off from that, in which I take the same identity and I either isolate the sine squared or isolate the cosine squared. And another one I found comes in handy specifically when you're doing the BC class. Your double angle identity for sine. Sine of 2x is 2 times sine x times cosine x. I know you probably studied about 50, 60, 70, whatever, a ton of identities. These are the ones I think you'll get most of the bang for your buck out of with your cal. Okay, start off with some derivative equations. First thing I'm going to tell you is the derivative of sine is cosine. The derivative of cosine is sine, or negative sine, excuse me. And I don't want you to be satisfied with just me showing it to you. I want you to actually be able to prove it or derive it or come up with it on your own. So first thing we're going to do is talk about a couple of common limits that I think you should know that'll help you in your proof as we go over. First one says that the limit as h approaches 0, sine h over h equals 1. And the limit as h approaches 0, cosine of h minus 1, all over h is 0. Please do not take my word for it. And then we also our definition for our difference quotient to find the derivative. I'm going to actually show you that these are in fact legit identities. So bear with me for a little bit. Okay, so I'm going to pull up my graphing calculator and kind of show you how those work. So the first little thing I thought you might want to know is that when you take the limit as h approaches 0, sine h over h is 1. So in my calculator in Y1, let me go ahead and deselect if we can here. Let me go down and deselect this one. I don't want to graph that. But we talked about as h approaches 0, sine h over h was 1. So let's go ahead and go to our table here. And right now, I have values that are missing. So let's approach 0 from both like the left side and the right. So if I'm approaching it from the left, I'll go with like negative 0.1 and negative 0.001, negative 0.0001. And again, if I did it from the right side, if I went positive 0.0001, hopefully you see that that does in fact approach 1 from both the left and the right, so that limits 1. If you wanted a graph, as I approach x here, I'm sorry, the y-axis, when x approaches 0, I get a value of 1. And then similarly, if I deselect this, and let's go down and do this next one. I guess I just graphed this here. Let me go back and do the table here. Okay, now my calculator's being stubborn. It's graphing still. All right, I'm not sure what's going on here, but here we go. Let's try this again. So I'm going to go second, graphs. Here's my table. And as I approach 0, it gives me some really creepy numbers here, like -5 times 5, or -5e to the -5, which basically means -5 times 10 to the -5th, which is 0.00005. It's basically the calculator's way of approximating 0. So again, that's not really a proof of these of those little bits of information, but we can prove it at another time if that's really something you want to see. But I just wanted to let you know about these so that you are good to do your proofs as we go on. So keep these guys in mind. They're going to come up during our first 2 proofs. So start off with the derivative with respect to x of sine x. Again, I'm using my difference quotient. Remember that your derivative is equal to the limit as h approaches 0, f of x plus h minus fx all over h. So since our function is the sine, I get the limit at 0, sine x plus h minus sine x all over h. Now we're going to play with this a little bit. And you might say, whoa, what is this? What's going on here? What did you just do? Maybe you remember another little identity from your pre-cal, your sum and difference identities, like sine of alpha plus beta was sine alpha cosine beta plus cosine alpha sine beta. That's called your sum. And then we also have difference identities. That gave me this little tidbit of information. For me, to memorize this identity, I just remember it as the old McDonald's song, only, okay, manipulated somewhat. For the sine, I basically think of it as like this. Old Man Winter had a sine, cosine, cosine, sine. It sounds ridiculous. It works. I've been teaching pre-cal and cal for a long time. Never had any trouble with it. So that sum and difference identity is where that little piece comes from. Now we do a little grouping. What I'm going to do is take this term here and this negative sign here, and I'm going to switch them. You might say, okay, why can I do that? Well, it's a little thing called the commutative property of addition. If I have 7 plus 5, I know that's the same as 5 plus 7. You know, if I have like 3 plus -2, that is the same as -2 plus 3. So basically all I did was just reverse their positions using the commutative property. Now what's starting to happen here is this. I can take these 2 terms right here that both contain a sine of x, and I factor that out down here, leaving me with the cosine of h, and no, that is not the hyperbolic cosine. For those of you going that route, we're not talking that. And then plus my cosine x times sine h. And now you might remember this. No. You might remember this little guy right here being one of those identities. So I'm going to separate it to get that identity. Sine x times cosine h minus 1 over h gives me sine x over 1 times cosine minus 1 over h. And then that was that identity, that little thing I showed you on the calculator. First one being a 0, and then the second one being a 1. So I get limit h approaches 0, sine x times 0, which is 0, cosine x times 1, which is cosine x, So therefore, the derivative with respect to x of the sine x is cosine x. QED, for those of you that want to learn a little Latin, stands for quod erat demonstrantum meaning thus it is demonstrated, thus it is proven. Okay, let's try the same thing. And I'm giving you what the derivative of the cosine is. It's negative sine. We're going to use those two little common limits or identities, whatever you want to call them, that are going to help us out here. So again, I start off with my difference quotient. Limit h approaches 0, f of x plus h minus fx all over h, where my f of x, my function, is this cosine. Now, there's also an identity for this. It is also a sum identity. Cosine alpha plus beta is cosine, cosine, sine, sine. And yeah, if you're in my pre-calc class, I've got a song for this too. And then it'd be alpha, beta, alpha, beta. And unlike the sine, the cosine does not retain its sign. So I'm about to use that identity on this part right here. Again, I want to do a little regrouping because I see this term has a cosine in it, cosine x. I want to move this cosine over here, so I want to do that commutative property again so I can get a little creative with my grouping again, so I can factor some stuff out. So again, all I did was use my commutative property of addition, switched the negative cosine with the negative sine times sine h. This time we factor out the common cosine, and then we separate again. And then again, that was that little special limits that we talked about. So I get cosine of x times 0 minus sine of x times 1, which is 0 minus sine x, which is negative sine x. Therefore, we know that the derivative with respect to x of the cosine is negative sine QED. So, 2 down, 4 more to go. These I'm actually going to use, now that we've established what the derivative of sine is and what the derivative of cosine is, I'm going to use that. And one of the things we talked about in the last lesson, the quotient rule to figure that out. So remember, when you're taking a derivative of some function f over some function g, that derivative is f prime g, not plus, but rather minus fg prime all over g squared. And we're going to use that using what we already know. Again, we know that the derivative of sine is cosine, and we also know that the derivative of cosine is negative sine, and that's going to be the route we take here. So, again, if my f right here is sine x, that's going to make my f prime cosine. If my g is cosine, that's going to make my derivative of the cosine negative sine. And whether you write your quotient rule like that or like that, it's basically the same thing. And I substitute in. So g times f prime minus f and g prime all over g squared gives us cosine squared, and then this double negative when you're multiplying here makes a positive, And hopefully you remember this little identity from your Pythagorean identities. That is the same as saying 1. So now we know that the derivative of cosine x is really 1 over cosine squared of x. And remember I talked about knowing those reciprocal identities? So the reciprocal of the cosine is the secant, so 1 over cosine quantity squared is really secant squared. So now we know that the derivative with respect to x of the tangent of x is the secant squared of x. Okay, let's continue. I guess I already wrote that. 3 down, 3 to go. So we're going to try cotangent, secant, and cosecant. If you want to try those on your own, go ahead. I'll give you a little head start. We are going to use the quotient rule again. This one's going to be cosine over sine. Secant is 1 over cosine. And cosecant is the reciprocal of the sine. Use a little quotient rule and see what happens. If you want to try them and pause, feel free to do so. Otherwise, here we go. So derivative with respect to x of the cotangent of x is the same as the derivative with respect to x of, again, I could do 1 over the tangent, but I think you'll find it's a little easier to go with cosine over sine. And again, we're going to do a little quotient rule. Here's my f, here's my g. So again, I need an f prime g minus fg prime all over g squared. Let's go and order our components. So my f is the top function, cosine. So my derivative, which we've already proven, derivative of cosine is negative sine. My bottom, my g, is the sine, and the derivative of sine is cosine. And let's do a little quotient rule here. So f prime is negative sine x times my g, which we said was sine x, minus f, which is cosine, times g prime, which is also a cosine. So that all over my g, or my bottom, squared. So that's going to give me a negative sine squared x minus a cosine squared x all over, let's write that sine of x squared like this, sine squared x. Now you might say, oh, it's not quite the Pythagorean identity like we had last time. Let's factor out a negative 1 on top, which will give me a positive sine squared plus cosine squared all over sine squared, which gives me negative. And again, sine squared plus cosine squared is the Pythagorean identity for 1. So I get negative 1 over sine squared. And again, the reciprocal of sine is really the cosecant, so that makes the negative cosecant squared of x, which is in fact the derivative of the cotangent. 2 more to go. Derivative with respect to x, secant x, is really the same as deriving with respect to x. 1 over cosine. Again, a little quotient. There's my f, there's my g. So f, that's not f prime, f is 1 So the derivative of the constant 1 is 0. My bottom function is g of x, which is the cosine. Prime will be the derivative of that, negative sign. And our derivative, remember, is fg minus fg over g squared. Prime the first, prime the last. And I get f prime, which we said was 0, times, really it doesn't matter what g is, but I'm going to write it anyway. Cosine, the reason it doesn't matter is because when I multiply by 0, it's going to become 0 anyway. Minus my f, which was 1, times my g prime, which was negative sine, all over our g squared, and g is cosine, so I get a cosine squared. So I get 0, negative, negative times 1 is going to be plus sine x over cosine squared, or sine x over cosine squared. So technically you could say the derivative of the secant is sine over cosine squared, but I think we can write it in a little more favorable light than that. So we're going to do a little algebraic manipulation here. So I'm going to go and write this cosine squared on the bottom and the sine on top. I'm going to write this as 1 over cosine times sine over cosine of x. Now, again, yeah, because if I were to multiply this back, I'd be right there. So really all I did was just separate the cosines using a little multiplication. And again, your identities, 1 over cosine is the secant of x. And then sine over cosine, we've talked about already. That's the tangent of x. So the derivative with respect to x of the secant of x is secant x tan x. And lastly, the derivative with respect to x of the cosecant, which is the same as deriving 1 over sine, which is its reciprocal. And there's my f, there's my g, so we set up all the components that we need for our quotient rule. F is 1, f prime is 0, g is the bottom function sine, its derivative cosine. So our derivative, remember, fg over g squared, prime the first, prime the last, and minus. So our f prime is 0 times our g sine minus our f, which is 1, times our g prime cosine, all over our g squared, which will be sine squared. So I get 0 times cosine, which is 0. Negative 1 times cosine is negative cosine, all over sine squared, which is negative cosine over sine squared. And I'm going to do a little separation like we did last time. So I'm going to go, this is the same as taking 1 over sine, negative 1 over sine. You can put the negative with either component, it doesn't matter. And then cosine over sine, which gives us reciprocal of the negative sine here is the negative cosecant, and then cosine over sine is cotangent. Therefore, the derivative of cosecant x is negative cosecant times cotangent. For me, doing stuff like this is kind of awesome. I like knowing where stuff comes from, being able to prove it and stuff like that. I hope you do too. So there's the punchline. Now, memorizing these might be kind of hard for you. I'm going to show you a really easy way to know all the derivatives of sines and all that stuff. It's really kind of cool, and I used kind of a unit circle model for it, but typically what I did that helped me out a lot is I memorized the first three. The derivative of sine was cosine, tangent was secant squared, and then the secant, he was kind of cocky, he liked to say his own name, so it was derivative of secant was secant, and then tangent, because there's like a relationship with the derivatives of tangent and secant. So I memorized those three first, and then all I did was this. You see how here, this is a sine, this is its co-function, this is its cosine. So basically, when I'm deriving a like here, this is a cotangent and a cosecant. All I do is, you'll notice the sine, the tangent, and the secant are all positive. So all of the co-function derivatives are all negative. And if I know that the derivative of sine is cosine, I either add a co to it if it doesn't have one, or I take one away if it doesn't. So, like here, if this is a cosine, it is negative sine. So I took the co away from here. Here, if derivative of tangent was secant squared, this is a negative and a cosecant squared. If derivative of the secant was a positive secant and a tangent, then its derivative was a negative, and instead of secant, we do cosecant, and instead of tangent, we do cotangent. So, again, probably takes a little practice to do. One of the best things you could probably do is to make yourself some flashcards, like 6 little flashcards. And on one side, maybe write derivative respect to x, sine, and then on back, write what its derivative is, cosine, you know. Maybe you write like derivative with respect to x, tangent x, and then on the back you write that that's secant squared. And using those flashcards, going over and over and over it again, it takes practice, but you'll get better with it. So, I talked about like deriving sine and cosine and a little pattern I have, and I said it's kind of based on the unit circle. Let me show you something here. I know this is my x-coordinate right here. This is my x-axis. If you remember earlier when we were talking about it, we talked about that sine of whatever angle was y over r, and r was 1, so sine was really your y-coordinate. So this y-axis is really your sine. And remember how we talked about that the cosine of theta was x over r, and r was 1, so it was really your x-coordinate. So cosine is associated with x, so this would be my cosine axis. And if going up is positive sine, down here is negative sine. And if going right is positive cosine, going left is negative cosine. And if you just go around the circle here, you've got all your derivatives. What is the derivative of sine? Go clockwise. It's cosine. What is the derivative of cosine? No, it's negative sine. What is the derivative of negative sine? It's negative cosine. And lastly, what is the derivative of negative cosine? Right back to the sine. Kind of a cool little deal, and it's something I use. And when we talked about integration in later units, it's basically the same little graph, only you go in reverse. Really kind of cool stuff. So, okay, I'm going to jump off my soapbox here for a little bit and just show you some math. But that's a pretty good way to remember those. So, derivative with respect to x, dy dx, if y is x sine x. Okay, this is going to be a product rule. Here's my f. Here's my g. So my f prime is going to be the derivative of x, which is 1. My g prime is going to be the derivative of sine, which we just talked about was cosine. So then Y prime is FG, FG, prime first, prime last, and plus. Again, why am I using product rule? Because I have a function f and a function g and being multiplied. And you might remember from the lesson I showed you on the product rule, I said, you know, sometimes you can just distribute and multiply, or distribute and do your power rule, and you don't have to use the quotient rule. But I said sometimes you will have to use the product rule. This is one of them. You can't just say, well, y prime is the derivative of x, which is 1, times the derivative of sine, which is cosine, and say my y prime is just cosine x. You can say it, but it's not an accurate thing to say, so don't. So I'm just going to do my product rule. So my dy dx, if you want to call it that, or if you just want to call it y prime or f prime of x, either way. So my f prime we said was 1 times our g, which was sine x, plus our f, which was x, and our g prime was cosine x, which gives me sine x plus x times cosine x. One product rule in the bank. That one is done. Okay. Again, using our derivatives, and this time, since it's division, a little quotient rule. Here's my f, here's my g. So my f prime, derivative of the top, derivative of sine is cosine. My g prime, derivative of 1 is 0, derivative of cosine, negative sine. And our dy dx, or y prime if you prefer, is, remember, fg over g squared, prime first, prime last, and minus. And then we just plug in all of our components. So f prime is cosine times g, which is 1 plus cosine, minus f, which is sine, times g prime, which is negative sine, and then all over g squared. Our g is 1 plus cosine, quantity squared. I'm not going to distribute that on the bottom. Again, when we were talking about quotient rule, I said typically I don't, because in multiple choice they usually just leave the bottom alone. You'll see another reason why I'm not going to mess with that here in a minute. So I distribute the top. Cosine times 1 is cosine. Cosine times cosine is plus cosine squared. Minus makes plus sine squared x all over 1 plus cosine, quantity squared. And again, this is one of those things I just know. Sine squared plus cosine squared, or if you do your commutative property, cosine squared plus sine squared, that's 1. So I get cosine x plus 1 over 1 plus cosine, quantity squared. Again, using our commutative property, cosine plus 1 is the same as 1 plus cosine over 1 plus cosine squared. Cancel this on top, leaving a 1 with one of those. I get an answer of 1 plus 1 over cosine. So again, problems like these, you have a little product rule, a little quotient rule, and then some trig with it. I think this is, no, we got 2 more to go here. So here, f double prime, so let's go here. So if f of x is secant x, and again, once you get better at this, you'll learn these. We talked about the derivative of secant being, this is the one that likes to say his own name, so it's secant times tangent. But again, I want f double prime, so we're going to have to do a little product rule, this being my f, that being my g. So if f is secant, f prime is secant x tangent x. Our g is the tangent, which makes its derivative secant squared. So f prime is going to be secant x tangent x times g. Remember, it's f prime g plus f g prime, and I'm just plugging in this information here. So our g was tan x plus f, which is secant x, times g prime, which is secant squared. So f prime of x, or f double prime of x, is really secant x times tangent squared x plus secant cubed. Now, if all I asked you for is the second derivative, we'd be done. But I didn't. I asked you to evaluate the derivative at pi over 4. So all that kind of trig stuff you did, hopefully coming back again. Now, here's the thing. Let's put this all in terms of sines and cosines. I think you'll be pretty happy. So again, at pi over 4, sine and cosine were both root 2 over 2. Let's just go with that and see what happens. So when I say secant of x, I know that's really 1 over cosine, but instead of x, the x value we're going to plug in is pi over 4 times tangent squared, so that's going to be sine pi over 4 over cosine pi over 4 squared, because it's tangent squared, plus secant. Well, we already talked about secant being 1 over cosine of pi over 4, and that's going to be cubed. So that makes 1 over root 2 over 2 times root 2 over 2 times root 2 over 2 squared plus 1 over root 2 over 2 cubed. Okay, let's erase a little bit here so we can finish. No big deal, easy peasy. Little complex algebra coming on, but we can handle it. So when I take 1 and divide it by root 2 over 2, that's the same as 1 times the reciprocal, which makes 2 over root 2 times, notice how the numerator and the denominator are the same, so that makes times 1 squared, which is 1, so times 1. And then plus this, again, I'm going to do a little reciprocal work. So 1 divided by that is the same as 1 times 2 over root 2 cubed. So that's going to give me plus, basically on top, it's going to give me a 2 over root 2 cubed. So let's rationalize. So again, we're going to do a little scratch work off to the side here. Again, this is good, just doing a little algebraic manipulation and dealing with some unpleasant fractions and roots and stuff like that. It's kind of good for the soul, so let's go ahead and keep going. So let's take a look at this piece right here. Root 2 over 2 times 1, sorry, 2 over root 2 times 1 is really 2 over root 2. And then when we rationalize it, that gives me 2 root 2 over 2, which is, well, that's just 2. Okay. And then here, again, I've got this 2 over root 2. And we already talked about how if I take 2 over root 2 and rationalize it, that makes 2 root 2 over 2, which is really just root 2 cubed, which is basically 2 plus root 2 times root 2 times root 2. And root 2 times root 2 is 2, so I get 2 plus 2 square root of 2. And we're done. Again, a little bit more complex, but you know, you need to stretch your algebraic legs a little bit. And lastly, again, I'm going to go ahead and draw that little graphic I had. Remember that your y-axis, your y is your sine, your x is your cosine, your negative y is your negative sine axis, and this is your negative cosine axis, and then this is how you derive. And please remember that it repeats every 4. So like if I start deriving sine, I derive it once, twice, 3 times, and 4 times, and then I'm right back where I started. That's the key here. Now the notation. What this means, d87 dx 77 of sine x, it means I want you to find the 87th derivative of sine x. Now the last thing I want to do is, okay, so sine is cosine, and then negative sine, then negative cosine, then back to sine. That's the last thing I want to do. So really what I know is this. I know these derivatives repeat after 4 iterations. So basically I'm going to take 87 and divide it by 4. Goes in there twice, no remainder. Goes in there once. And I believe it gives you a remainder. That gives me, what, 84? So I get a remainder of 3, which basically tells me that is going to be the same as finding the triple prime. So there's derivative 1, takes me to cosine. Second derivative, negative sine. Third derivative, this is negative cosine. Really cool stuff. Last one, the 100th derivative with respect to x of cosine. So that tells me I'm finding the 100th derivative. And again, remember that if I start here at cosine, I derive once, twice, 3, 4 times, and I'm right back where I started. So I take 100 divided by 4, that's 25. With the remainder of 0. So what does that mean? What that means is a remainder of 0 is that the derivative 100 times of cosine, this thing's going to go around this little circle of derivatives here 25 times and end up right back where it started from. See, if I go remainder 1, remainder 2, remainder 3, remainder 0, you start where you finished. Or you finish where you started at. So I hope this made a little sense to you. I promise if you're a student in my class, we're going to go over this a lot more and practice some more. If you're not in my class, hope it helps and maybe gives you some questions you can talk with your own teacher about. But I hope you have a good evening and enjoy.